In 1894, Professor J.C. Bose showed that lead sulfide can be used to detect radiation, and at that time the idea of semiconductor was not known. Forget about doping. So this was summarized by Neville Mott in his one of the lecture, that J.C. Bose was at least 60 years ahead of his time. In fact, he had anticipated the existence of p-type and n-type semiconductors. So I really, it's an honor to come and give a talk here, which is related to semiconductors. Of course, after that, a lot of things happened, several Nobel Prize, and but the crux of the matter is we should work in science to expand horizon of knowledge. Implication in technological development is very hard to figure out, obviously, because it has economics, it has society, and many other things. Scientists most of the time cannot control those things. So now what is my topic today is a semiconductor quantum dot, which is very interesting in the sense that it is a very controlled system. It's epitaxially grown in molecular beam epitaxy, and the whole avalanche of this work started with this PRL, which was published in 1994. So essentially, you take a gallium arsenic substrate in a ultra high vacuum chamber and deposit indium on that, maybe just slightly less than the monolayer required to cover the substrate. And the strain develops because of the lattice mismatch, and finally they form this kind of dots on the gallium arsenic substrate. The surprise is that if you take the photoluminescence characteristic of such material, you will get extremely sharp peaks, but many of them scattered around this wavelength. So immediately it was known that there are few things which are coming into picture. One is whether the electrons are localized in the dot, holes are localized in the dots, whether there is a variation of composition, whether there is a variation of shape and size of the dots. Everything will change the position of this PL. So that is very well known, and so many work has been done. It is summarized in this advanced material paper very well. Well, the question is that if you have such a system where you can control such things, obviously the problem which is shown here becomes an advantage when you have control on it, because then you have a controllable photonic device. So you can control the luminescence energy by controlling all these things which I mentioned. That means shape, composition, size, and everything. Okay, so this is of course the work which I am going to present are the thesis work of Orko, my present student Orko Vikas De, and earlier student Manjula Sharma. Manjula is in University of Delhi right now, and Orko made a very nice summary slide that that if you play with the composition of this indium gallium arsenic, so there are two extreme. One is gallium arsenic, another is indium arsenic, and if you assume that there is a spherical quantum dots, then immediately you will see that this this gap depends on the x, and if you change this composition, you can tune the gap, and you can reach ultimately the indium arsenic, which is 0.43 eV. So you have this play. You can also play with the size of the quantum dot. So if you reduce the size of the quantum dot, the levels which are discrete levels, they get separated out. I have not shown here the shape, that is actually goes in the scaling, the way these get separated. Now what is very trivial and simple and important is this diagram, that the position of the photoluminescence peak or their separation between them is the separation between these jumps. So essentially what I am trying to say that if you are measuring the separation between these peaks in PL, you can directly measure the effect of size and also the shape. But the absolute position of this PL peak dependent on the band gap. So all these parameters will help you to understand how things are working. The question is, can we find out composition inside one quantum dot? Is it possible? And can we determine the shape and size of this quantum dot in unambiguous way? So that's the thing. So if one can do that, then obviously there are other things to do to make it a technology. You can position those quantum dots at will wherever you want. You can tune all the parameters, and then finally on chip they should be able to talk optically, and that makes the chip faster. And of course, my previous speaker has already said that there is a huge push of display device and all that. But I'll stick to my first transparency that let us talk science. The applications will happen and we can't control most of the time. Okay, so the plan of my talk, which I have already started, so introduction is almost over, but I'll tell you why X-ray is important to find the shape, size and composition of individual quantum dot. And then we'll see how these novel properties can be tuned, and the tuning the indium arsenic quantum dots and the correlations with photoluminescence, direct correlation between X-ray measurement and the photoluminescence property. So it's a structure property correlation. And then we'll come, most of the talk will be on gallium arsenic, indium arsenic, but towards the end I'll also show you our recent results on silicon germanium quantum dots. Well, for silicon germanium quantum dots, I have had very nice collaboration with Professor S.K. Roy, IIT Kharagpur. Of course, now he is in SN Bose. And for the indium arsenic, gallium arsenic, the samples were grown in Cavendish lab in Cambridge, and my collaborator Ian Ferrer and David Ritchie. Okay, now X-ray actually has moved a long way, and the coherence, size, polarization, energy tunability, everything is possible with synchrotron. And the beauty is now you can have a size of the beam, of the X-ray beam, which is less than the size of your nano object. So only one nano object can get illuminated by the beam, and then if you sit in a Bragg reflection spot with a two-dimensional detector, you will get a fringes like this. The separation of these fringes are the distance of the faces in the opposite direction, and this immediately tells you the shape of the particle. And also this fringe separation will tell you the distances. So the shape and size can be determined from this measurement, just simply by illuminating one dot with one X-ray beam. And this is what is published. This was the first work here. A lot of work has happened since then. The problem comes in the different way, that as you can see, these are about 600 nanometer and also about 20 nanometer high. That's good enough to absorb the X-ray. The problem comes when the quantum dot size gets less than 10 nanometer, and the size of the quantum dot becomes something like 20, 30, 50 nanometer. That's the technologically important material. Then what happens? The X-ray actually goes through, because very little scattering will happen from such a tiny object, and that's the problem. Second problem is engineering, how to hold beam on the tiny dot when you are doing the measurement, because there is a thermal vibration. So that has been solved by putting it on a piezo and giving a active feedback, so that your measurement is done by shifting the sample continuously, so that it is always on the beam. But the main problem now remains how to do the diffraction from a tiny object where X-ray scattering is very, very little. So this is our topic. So one way to do that is by increasing or by reducing the angle of incidence. So you have grazing angle of incidence. I'll tell you why. Because as I have showed, all these dots are on the top of a gallium arsenic substrate. So the idea is you must reduce the signal from gallium arsenic. It should be coming from the top surface where dots are. So that can be done by reducing the incident angle of X-ray, and as you know, the refractive index of any finite material is slightly less than that of vacuum in X-ray, and so you have a finite critical angle. So if you are around that critical angle, then X-ray doesn't penetrate much in the bulk. So all this scattering comes from the surface, and there are several types of scattering which happens. I'll not have time to discuss all of them, but essentially you have these different types of scattering processes which happens. The X-ray comes and gets scattered from the surface. It gets scattered from the quantum dot, and of course the nature of scattering can be various types, which can be summarized in these 4 types of thing, and these are details. And then by measuring all the X-ray scattered beam on a detector, you can figure out the composition of this quantum dot and also the shape of the quantum dot. That is what I'll convince you. The problem still remains that once you have this incident angle very small, then obviously the footprint of the X-ray beam will be larger on the surface, and as a result it will illuminate the large number of quantum dots, unless you make sure that all the quantum dots are out, only one is remaining, but that will reduce your scattering intensity. So these are the games which are going on. And so our sample, the first sample which we studied with this technique, is a variation of quantum dot density on a same substrate, because that is very important to understand how the composition changes simply by changing the growth mechanism on identical conditions. So it is grown on the same substrate, same time, but simply by keeping a temperature profile, you can change the density of the quantum dots in one portion of the substrate with respect to the other, and that changes the average diameter and height and everything. So this is what we published. This was Manjula's one of the paper. The problem still remained there in the sense that photoluminescence comes from the bottom quantum dot layer, and the structural information comes from the upper layer, and the assumption is these two are conformal, and the information you get from photoluminescence and information you get from the AFM measurement and X-ray measurement are can be correlated. So that was the problem which we said in our paper. Nevertheless, the technique went through very nicely. All you have to do is measure 400 and 200 reflection. Rest are details. If you take ratio, then you can directly extract the indium profile from there, because you know for 200 the structure factor of gallium and arsenic, they are adjacent in periodic table, so they just cancel each other. Indium is much higher, so only indium intensity comes in, and that is what helps us to get the height profile, as a function of d value. I mean, you are dealing with a composition variation from gallium arsenic to indium arsenic within the dot. So you can extract the composition of that indium composition in the quantum dot as a function of height. So that can be extracted from all this measurement, and we showed that it can be correlated by PL measurements of those samples. Now, at this point, as I said, that PL is coming from the buried layer, and the X-ray and AFM measurements are done on the top layer. So, there is a questionable linkage between them. So, we became ambitious, and we said that, well, that was a success. So, ORCO really did lot of measurements on this exposed quantum dot. So, these are uncapped, just indium arsenic exposed quantum dot, and photoluminescence was also measured on that. So, it is a directly structure property correlation now. And similar measurement which Manjula did, but now we have a better control that all the information which is coming from X-ray can be cross-checked with AFM and can be cross-checked with the PL, and this is we just submitted for publication. So, again we have this composition, say 200 and 400 reflection. From there you can find out the indium concentration as a function of height of the quantum dot, and then for all these three sample, one is uncapped, another is 5 nanometer capped, and another is 30 nanometer capped. So, this is also very interesting technologically, that when you put gallium arsenic cap on this indium arsenic quantum dot, there is a mobility of the indium simply because of this capping. But capping is important to sustain it for long time use in the technological environment. So, we did all this measurement, and finally, what was surprising is we found that from the shape of the X-ray scattering line shape, we could see that it is not a circular disk or a quantum dot having a circular base. It's an elliptical base, and those details has been done, and of course, it has been cross-checked with AFM that in one side it is 44 nanometer, the other side is 25 nanometer. So, it's the eccentricity is quite good in such things, and that gave us another handle how the eccentricity changes the photoluminescence property. So, from all this detailed modeling, we could really figure out the composition of the quantum dot as a function of height. I will say these are average quantum dot, because many of them are illuminated by X-ray. Now, we are trying to see whether we can reduce this number of illuminated X-ray dots because of the availability in Petra 3, DAISY, very intense X-ray beam, and we can grow the sample in such a way that we can reduce the number of quantum dots which are getting illuminated by X-ray beam slowly. So, right now it is about 10,000 quantum dot which are getting illuminated. So, we come to 1000 and then 100 and then finally 1 maybe. So, we will get composition variation and this kind of plot from single quantum dot, and this is the kind of PL which comes when it is uncapped. The moment you do the capping, of course, the PL intensity goes up, but what we found, the position of these peaks are more or less independent of this capping, and that makes our life simple. And then, as I told you in my earlier transparency, by looking at the position of these peaks, you can find out the size, and of course, you can cross check with the X-ray and put this together, and then also the composition which is coming out from here can be extracted from PL, assuming that the excitonic volume, the amount of quantum dot is excited, the exciton is stationed around the base of the quantum dot, and keeping all this in mind, you can really correlate them pretty well, and this is what we have just submitted for publication. Well, now the last part, I think I have 10 minutes, 5 minutes, okay. So, I am almost done. So, the last part of my talk is homegrown sample. This is silicon germanium in Shah Institute. and Manjula did fantastic work to set it up, the whole thing. And then, of course, we could control the silicon germanium growth parameters so well that, as you know, the silicon, everybody wants silicon to be optical material, but it is not. And because it is indirect band gap and all this known story, you can make it in principle a optical material by making quantum dot of germanium inside silicon, because the moment it is quantum dot, these are discrete levels, as I showed you, and discrete levels should not be related to this indirect semiconductor physics. And this was the motivation, because people have shown this chain in 2010 that the germanium, when you deposit at slightly lower temperature, it actually sinks inside the silicon, and instead of quantum dot which is positive, you get an inverted quantum dot. And this is very nice, because as it is going inside, so capping and other things will not be required. And he also did in TEM the profile and to find out how the germanium content is. Now, of course, we were interested to grow that, and finally we could also grow, Manjula could grow it, and by doing this silicon germanium compositional profile, we could see this, these are grown on superlattice, and this inverted quantum dots of germanium is growing one top of the other, which is expected. And so again, we did this X-ray scattering to find out the composition and all that. But at this time, for silicon and germanium, you are not lucky. There is no, these materials are not cancelling each other like the gallium and arsenic. So you have to do a trick of anomalous scattering. So you have to tune the energy of the X-ray beam so that we come to the absorption edge of germanium, and as a result, the scattering from germanium can be tuned. And by tuning that, one can find out this profile, and from there we could again find out all the this shape of the germanium inverted quantum dot, and also the composition of that.